Okay, so in this problem, we have two masses and we have, so I'm just going to kind of draw everything out. Here's mass 1, here's mass 2, and, oh, whoops, actually the top one is mass 1 and then the bottom one is mass 2. And are they both of length L? We know M1 is 4 kilograms, so let's write that down. And M2 is 3 kilograms. And the length is 0.500 meters. And they're collinear. So M2 is traveling at V2 is equal to, was it 4 meters per second? And we want to get the tension in string 1. And then which one is string 1? It's the top one. And so we want this tension here for mass 1. So let's do a free body diagram. Basically the only force is acting. I assume this is not like vertical. Let's read. Yeah, it doesn't really say anything about vertical or gravity, so I can kind of assume this is in a horizontal plane. So basically we have the tension force acting, that's the only force. So we can do the sum of the forces is MA, the sum of the forces is just tension, and then A is centripetal, so A is V squared over R, where R refers to the distance from the mass to the axis of rotation, which is just 2L. So R, the radius, is equal to 2L. And so, yeah, that's what we want to do. And then let's be careful. We know M is equal, we're doing M1, and we know the velocity is, ooh, why did I write that down as V2? Ah, I see, because we don't actually know V1. So we actually need V1. So if they're collinear, then that means they have the same angular frequency. So omega is V over R. So V1 R1 is equal to V2 over R2. And so we know, and then these R's are the distances from the mass to the axis of rotation. So we know V1 is equal to V2 times R1 over R2. So it's V2 times, which is what we know, times R1. R1 is at a distance of 2L, and then R2 is at a distance of 1L. So we know that V1 is going to be moving at twice the speed of V2. So we can plug that in. So M1 times 4 V2 squared divided by 2L. So that's 2 M1 over L V2 squared. Now I can plug that into a calculator. So, oh, actually I don't need to, because it's, all the numbers are nice here, I don't think. So let's see, 2 times 4 is 8, times 16 divided by L. So 8 times 16 divided by 0.5 is 256 newtons. And oh, that's slightly different than somebody else did this problem, and so it's slightly different their answer. So I'm going to double check it. But I feel like this seems right, so I'm not sure. Yeah, so I mean, if we're just, so 2 times 4 is 8, and 8 times 16, yeah, divided by L is 0.5. So I think I do stand by my answer for now, but I'll keep my doubts in mind. Oh, I see what happened. So it did actually say vertical. so so I need to modify this equation. So the tension is, so you don't just have the tension down, you also have the weight down. So you have tension plus weight is equal to this. So tension is this minus weight. So that's actually a pretty easy modification. So minus weight. So it's going to be 256 minus M1G. So that's 256. Wishful thinking. I thought I didn't want to see the vertical word, so I missed it. Minus 4 times 9.81. So I got 217 newtons. Okay, that's okay. That was a pretty easy modification. And then we want to get the tension in string 2 at this instant. So again, let's do the free body diagram on M2. So we have, this is string 1. So it has tension T1 and this has tension T2. So what's pulling on mass 2? We have T1 pulling this way and the weight pulling down, and then T2 is pulling like this. And so, yeah, and then we want this force to be bigger, the force down to be bigger because it's moving in a circle. So we know, let's make this direction positive, even though it's down. Again, you don't have to if you don't want to. And then, oh yeah, let's relabel this as T1. So T1, so we have the two forces down, T2 plus weight minus T1 is mv squared, and that's v2 and m2 over r. In this case, the r now is L. And so you can get that T2 is equal to, and then let's just solve algebraically. So we have m2 v2 squared over L plus g, because this is going to be mg. Oh yeah, minus g actually. And then we want to add T1. So just algebraically, so plus T1. Okay, so now let's plug this all into a calculator. So we have 3 times V2 is equal to 4, so that's 16 divided by 0.5 minus 9.81 plus T1 is 217. So I get 717. So that has more tension in it. And then, so as you go faster and faster, I mean, you can see that T1 as a function of velocity, I mean, let's just kind of put this in terms of velocity. So we have m2 times v2 squared minus divided by L. Sorry, and I'm trying to just answer this question about, what happens, which string is going to break first. So T1 is M1 4v2 squared over 2L minus M2G. Simplify this a bit so the relationship becomes clear. Wait. Oh, shoot. This needs to be like this plus T1. Yeah, my bad. So actually, look at my calculation that I did here. Oh, yeah, I made a mistake. this is 288. Let's just double check that. Sorry, 284 newtons. I figured that out by using kind of unit analysis in my head. So that's 284 newtons, and yeah, so we can take we're taking M2, and we only want to multiply it by this, plus M1 B 4V2 squared over 2L minus M2G. Or that was M1G. Okay, now if we simplify this a bit, we can take out a G, so we have an M1 plus M2 times G times negative G, and then we have a plus V2 squared over L times M1 plus 2, or sorry, M2 plus 2 M1. And so you can see, and then we want to compare that with the tension here. And then you can kind of see that this one has this additional term with this V squared. I'm not sure. I think it's going to take me a while to like kind of talk through the comparison. But I think if you kind of compare these, you can kind of see that that no matter what, that the tension in the last string is going to be larger. And so, I mean, and it also kind of just makes sense that it needs to support more Yeah, I mean, maybe it's best just to look at it algebraically, but another way to reason would be there's nothing really special about this example of this velocity. This tension was bigger than this one, and then that's always going to be the